All right, so now that we know what Euler paths and Euler circuits are, again, we're using every edge exactly once. A path does not have to begin and end at the same vertex. An Euler circuit must begin and end at the same vertex. How do we know if there is one? Like, do we have to go through the process we went through on the last page of notes where we just keep trying things, and once we try things so often we just kind of decide it's not going to work? Or are we just going to stumble across something? Are we going to get lucky the first time? How is that going to work? Thankfully, it's not all just about trial and error. So for any connected graph, if every single vertex is an even vertex, then the graph has at least one Euler circuit. And an Euler circuit can start at any vertex. Okay, so if you look at all the vertices and they're even, then you know there's an Euler circuit. Start anywhere and you'll find one. All right. If exactly two vertices are odd, there is not an Euler circuit, but there is at least one Euler path. Okay, and you have to start at one vertex of odd degree and end at the other. That's the rule. All right. If there are more than two odd vertices, then there are no Euler paths, there are no Euler circuits. Okay, so this is one of the things you kind of have to keep in mind. One of the things that I'm going to ask you to start to get absorbed into your brains. Okay, if everything is even, there's a circuit, start anywhere. Two odd, there's a path, start and end at an odd. If there's more than two odd, game over. Neither one exists. Okay, so using that information, we're not going to find the Euler paths and Euler circuits. We're just going to decide if there is an Euler path or an Euler circuit or neither one. And we're going to give just a little bit of reason why. So I'm going to pull out a color here that'll stand out a little bit more than the black. Okay, so looking at the vertices of this graph and the degree of each one, you will notice that the degree of every vertex is degree 4. Okay, so all vertices are even. And so looking at number 1 up at the top of our Euler theorem there, if all graphs are even, we have an Euler circuit. Okay, so this definitely has an Euler circuit. Let me get rid of that little ditty there. Euler circuit. Okay, we know that. And then we could start at any vertex and find one if I had asked you to do so in this example. I didn't. Okay. Looking at the next graph, so again, kind of starting at vertex A, there's a vertex that's odd. B is also odd, so we're in the running here for an Euler circuit. Vertex C has degree 4, vertex D has degree 4, vertex E, there's a problem, degree 3. F has degree 4, G also has degree 3, so we're talking more than 2 with odd degree. And so this has neither an Euler path nor an Euler circuit. Okay, so as soon as, and actually once we found the third one, we could have called it game over, but I was just being thorough and making sure we get all of them in case you were looking at them in a different order than what I was. All right, moving down to the next one. Again, we need to look at the degrees of the vertices. Anything that's odd, those are kind of the ones you need to make a note of. So I'm noticing that D has odd degree, F has odd degree. Remember C, the degree there is even because you count the in and the out of the loop as degree 1 and then degree 2, 3, 4, 5, 6. So we're 6 there. E, same thing, it's got degree 4, it's got 4 ins and outs. So this is 2 with odd degree. And if we have 2 with odd degree, this must have an Euler path. And if you were going to find one, you'd have to start at either vertex D or F and end at the other one. And again, if you want to try it out, go for it. You do need to, by the way, on a loop, you do need to cross that. So if you were going to list those vertices, let's say you started at F, you'd go F, B, C, and then you could list C again, for example, which would say go around the loop, and then go on to vertex D or go on to vertex A or whatever you choose. Just kind of as an FYI. All right, for the next one, again, looking at the degrees, I notice C has degree 3 and E has degree 3. All the others are even, so we've got 2 with odd degree. This is an Euler path, once again. Start at C or E, end at the other. And then last but not least, looking at this other graph here, counting the degree of all of those vertices, B, C, and E all have degree 2. D, A, and F all have degree 4, so these are all even. This must have an Euler circuit. Okay, and in the next video, what we're going to look at is, okay, now that we know we have an Euler path, or we know we have an Euler circuit, is there a quick way to find one without using kind of trial and error? So you can still, now that you know there is one, you can still take a wrong turn. We're going to come up with or study a method to make sure we hit one every time.